Alright, so I'm really happy that this actually started working, but for those of you who didn't have any notes today over 1.6, I want to talk about choosing a good display. A few of you did have some notes over that today, so you can kind of fast forward in this video to the 1.7. But when we're choosing a good display, there are really a few different types of displays we've already talked about. For instance, sorry about the coughing thing in your ear, I'm sure that was annoying. We talked about one variable displays. So we already know how to display data in a one variable way, and we have all kinds of things like stem plots and box plots and dot plots and what else did we have? Histograms and bar graphs and circle graphs. Lots of different types of displays. Okay, well, in this section they want to introduce two variable data. And how would you display two variable data? So, for instance, the ones that they want to bring up to you are scatter plots and line graphs, which are basically the same, except you've got lines connecting the dots. So, for instance, they show you in the book two different graphs. So let's see here, zoom in. The first one on the left is obviously a scatter plot, and the data that you see up above there are is the population data for the town of Boston. Okay, and then they've actually connected them together. This makes a line graph. Not a whole lot different between them, but when you put the lines in, then it's easier to tell the slopes of the lines. You can use bar graphs to show scatter plots, but the drawback to those is the fact that you can see on the x-axis how there's 50 years between these two, but only 10 years between these. Now the bar graph doesn't show that. It does not show the distance between the data, except for you actually reading it. The display of the data really comes in clearly when you see these, and you can see, okay, well that's 50 years in between there, but it's only 10 between those. Now, we talk about rate of change, average rate of change, and the average rate of change has a fancy word for it, slope. Okay? So you guys know how to find slope. It's y2 minus y1 over x2 minus x1, where you may see rise over run. And yes, the reason I misspelled it is so that you would think in terms of the y values being on the top. Believe it or not, there's a handful of trig kids every year that get that wrong, and it's a simple thing. Obviously, a positive slope or a positive rate of change means it's increasing, and a negative rate of change means it's decreasing. So, this should all be review. If you look back in the book, you'll see in the textbook just a couple examples on finding slope, but it shouldn't be all that hard for you to do. You've done it all your life, or at least in Algebra 1. Probably in middle school too. So they're going to ask you different questions like what types of graphs are the most appropriate. So if I were you, I would look at questions like 4 through 9. Now in those questions 4 through 9, it could be more than one correct answer. So don't think, like for instance question 4 says shows individual data points. Well, that could be stem plots, scatter plots, line graphs, or dot plots. Okay, so as you go through there and look at those, make sure you understand. I mean, for instance, shows the 5-number summary, question 7, well that's only a box plot. So that's so look at those 4 through 9, make sure you understand how to do those along with the slope. And we'll look at question 12 in class, so make sure you ask me about question 12, because it's really important that you understand how to go from a frequency distribution, as I said in class, the frequency table back to a set of data, and that's going to be, you're going to be tested over that, so make sure you understand that. Okay, we really want to get to section 1.7. In section 1.7, we're talking about variance and standard deviation. We know how to measure the center of a data set, but we really need to understand how to measure the spread of a data set. So, for instance, they show you in the book here 2 different basketball teams, and they've got all the girls' heights listed there. Now, both of them, as you can tell, have the same range, 69 to 79, so they have a range of 10. But, and each of these teams both has an average height of 74 inches. But clearly you can tell that the group on the left, the Macaws, is more spread out, and the group on the right, the Sweet Dreams, are more concentrated right here in the middle. So there's got to be a way to measure the spread of the data and be able to say, this one is more spread out than this one. Some type of comparison between the two. Well, there is, and it's called standard deviation. And we want to talk about how you get there. Here are the steps that you need. Okay? And I'll show you the formula, but here are the steps. First, you calculate the mean of the data, the average. Then you find what's called a deviation, or a difference of each value from the mean. What does that look like? That's when we get into the data, you'll see that they actually took every data value and subtracted the average. So you might see something like x sub I minus x bar. That represents what's called a deviation. Okay? Now, how do we find an average? Well, typically you add up you would add up all those numbers called deviations and divide by the number that you have. Well, there's a problem with that. When you add up all the deviations, some of them are positive and some of them are negative, and every single time you do that, they all add up to 0. That doesn't make a whole lot of sense. So how are you going to give a value to something if but the sum always turns out to be 0? Well, so in order to fix that, we square each deviation. Right there it says square each deviation. Now the reason we square them is so that we can make them positive. And then we're going to add them all up. Now, when you do the next step, it says divide the sum of square deviations by n minus 1. Now, you might say to yourself, okay, wouldn't you want to divide by the number of values that you have? Why would you divide by one less than that? Well, for a bigger discussion that's going to happen in AP Statistics next year for you, these are called degrees of freedom. I'm not going to really go into it too much, but because we are dealing with a sample, and not an entire population, we cannot say that we are accurate to n degrees of freedom. So in other words, we are not going to divide by n, we are going to divide by 1 less than that. So the standard deviation that we're going to find is actually a little bit bigger. I'm sure I'm going to have to explain that in class or talk more about that. This short little video is not going to give you a very good understanding of why we're dividing by n minus 1. But I will show you the 2 things in the book, or you can look in the book and see the difference between population standard deviation and sample standard deviation. This one that they're describing right here deals with a sample. Well, when you do that, you've got something called variance. So when we refer to variance, that would be the end of step number 4. With the exception that that is not the description we want. We want what's called the standard deviation. So in other words, we're going to take the square root of the variance. After we have squared all these numbers and added them all up, when we did our division, we do need to get it back down to a linear dimension, so we need to square root it. By doing that, when we take that square root, we get what's called the standard deviation. So if you follow along in the book, here is the example that they have. They said find the standard deviation, the variance and standard deviation for the basketball team called the Macaws. So if I were using my calculator, I might put in list 1 in my calculator, I would put this data right here. Now, in list 2 over here, I would put, list 1 minus the average. What was the average there? 74, they said. And we would probably have to do the 1-bar stats to come up with that number, but they already gave it to us, so I'm going to use it. And then we would want to take the squares of those deviations. So obviously maybe they would do that in list 3 in their calculator. They would add up all those values, divide by the number of values, see how they divided with that, they took that 128 and divided it by 9 instead of 10, and then they took the square root, so 3.77. That is the standard deviation for the macaws. Obviously that number is going to be bigger than the one you find for the sweet dreams because they're more concentrated right around their average. And I know we're going to have more of a discussion about standard deviation because this is not the end-all to end-all of understanding about it. Okay, you have to think about it a little bit before you really understand it. Here's the formula that they have in the book. I'm going to zoom in so you can see it. Okay, it says take each data value, subtract the average. Well, that's called a deviation. And because some of these are positive and some of them are negative, we have to square them. After you square them, then you add them all up. That's what the summation sign says. And then you divide by n minus 1. This is what we call a variance, and you're going to see s squared to represent the sample variance. Well, when you do take the square root, you get the standard deviation. This right here is your standard deviation. Obviously, you can see that they took the square root of both sides. So here's this nasty, ugly formula. Oh, by the way, when you do your calculator's 1-bar stats, I guess I need to be able to spell, huh? 1-bar stats. One of those things in the list that you're going to find is S subscript X. That stands for sample standard deviation. I want to make this really clear, and I'll talk about it in class as well. Unless you're told that a data set is a population, you are always, I'm talking about tests, quizzes, final exams, quarterlies, whatever. Unless you're told that this is a population, you are going to assume that the data you are using is a sample. So every time you run the calculations for 1-bar stats, you're looking for S of X, which stands for sample standard deviation. If you want variance, all you have to do is take the standard deviation and square it. So you're saying to yourself, why would I do all of this if I could just do 1-bar stats in my calculator? I do understand where you're coming from when you say that, but I need you to understand what standard deviation is, not just how to push buttons on a calculator. So they took all the data for the players on the Sweet Dreams team, found all the deviations, notice they're a lot smaller, squared them. When they added them up, they got 52. That's a lot smaller than 128. Took that number, divided it by 9, right, because you're going to divide by 1 less, and then took the square root, so 2.4. So the Sweet Dreams had a 2.4 standard deviation, and the macaws had a 3.77, obviously a lot larger. Trying to think what I wanted to tell you next. Oh. Data that's more centralized is always going to have a smaller standard deviation. You can see this is starting to spread out, so that would be a bigger standard deviation. This one would be the biggest out of all of these because it's spread out the farthest from the average. Anytime you spread the data out really far, you're getting a higher standard deviation. They're going to ask you a question in the homework about creating numbers which have the smallest standard deviation. Well, if they were all equal, that would be the smallest standard deviation because the standard deviation would be 0. And if you want to make it the biggest, then you try to pick numbers that are really far apart from each other. Now they have a discussion here at the bottom about population variance. population variance, you notice that they're using the lowercase Greek letter sigma. All right, that lowercase Greek letter sigma is squared, so this must be the variance, right? It says population variance. And the difference you see down here is in the denominator. It says n. When you're dealing with a population, you have all of the data. There's no guessing as to what the standard deviation is. You know the data. So the little sigma that has been square rooted is obviously the population standard deviation. Now, we won't be using this a lot. It is in your 1-var stats. When you look in your 1-var stats, you'll see sigma x. All right? That is right underneath Sx. Most of the time we'll be dealing with Fx, right, for a sample, not dealing with the population. Okay, we'll talk more in class.